Thanks for joining my talk at the DIRA workshop at CBER 2020. My name is Zach Yu. I graduated last year from the University of Pittsburgh, and I'm currently working at Google on shopping attributes. Today, I'm going to present a work that originated from my BPhil thesis project at Pitt, and it was completed before I joined Google. The work is on interactive image search with attribute conditioned synthesis, which we call Syntharch. I would like to give special thanks to my advisor, Dr. Andriana Kowalska, who provided tremendous help to this project and my undergraduate studies overall. I would also like to thank other members on my thesis defense committee for giving valuable feedback on the work that led to its current shape, including Dr. Dajing He and Dr. Aaron Walker from Pitt and Dr. Marian Goh from Carnegie Mellon University. To start my presentation, I would like to give a little bit of context on the task of content-based image retrieval, or CBER. The volume of searchable images is rapidly growing in recent years, and measured by those indexed by Google Images alone, the number went up from 250 million in 2001, when Google Images was first launched, to over 1 billion by 2005 and over 10 billion by 2010. For online image search, we can use contextual information, specifically the tags surrounding the origin of the image, to proceed with the web search. However, sometimes we don't have those type of metadata and have to formulate the search based on the images themselves. That task is formalized as CBER. We know that CBER is in contrast to concept-based image retrieval, which retrieves from text-based indexing of images. Instead of using those image contents in concept-based image retrieval, we consider image captions, keywords, or the headings in response to the textual queries. Without those textual information, and I would say that the majority of searchable images we have might not have those textual information. The major challenge of CBER is therefore to establish a mapping between the user's high-level concept and the machine's low-level representation of the image. In particular, computer systems represent image as 3D tensors of dimension width by height, by the number of channels, whereas people understand images by the content, the objects, the perspective, and the composition, etc. Now, we know that there exists a cognitive gap between the user and the machine. To overcome this challenge, we consider from two directions. First, instead of accepting only one query for each search, we can allow the user to interact with the retrieval system in order to gain additional information regarding the target image iteratively. This helps us to elicit fine-grained queries when a large number of similar images are present in the database. However, we'll still need a way to bridge the image representations and to close the semantic gap even if we do it over time. For this, researchers found relative attributes to be helpful in transforming the machine's low-level image representation to high-level semantic attributes which can be expressed in textual form and understood easily by the user. With relative attributes, users can provide feedback on how some attributes of an image differs from that in another image. For example, as shown on this slide, we have images of three, or I should say diagrams of three devices and relative attributes of portability. With this attribute, we can make comparisons such as, for example, I want an image that expresses more portability than, say, the tablet. And then the search system will reason that the target is more likely to be the phone on the right as opposed to the desktop computer on the left. However, using relative attributes in textual form lead to additional issues. The first issue is that search system will then need to understand domain-specific semantic attributes. What I mean by semantic here is that some attributes are nameable and can be understood by the user in textual forms. Those are referred to as semantic attributes. As a result of the requirement of semantic attributes, prior systems can only work with labeled dataset with those attributes. And the appropriate attributes need to be chosen by someone with domain knowledge. For example, if you think of the attributes we have for images of products, say if it's a text for some kind of shopping search engine, then for different categories of product, you will imagine that there'll definitely be different attributes that we want to focus on in able to distinguish all the products. And to choose the correct set of attributes, we need domain expert to start. The second issue is that users need to understand the attributes in the same way as the system does so. So there's still somewhat of semantic gap. Let me show you an example. So some attribute like feminine or formal might be harder to define and to capture as compared to other like brightness or, for example, color. In fact, you can probably argue that brightness and color can just be extracted by some kind of hard-coded algorithm, whereas conceptual and abstract attributes like feminine and formal cannot be. Users need to be able to compare loosely defined attributes, including those abstract attributes, in the same way that the computer understands it. And if the user is giving inconsistent comparisons, then we are going to have ineffective search. To address these challenges of interactive image search, we propose Syntharch. Syntharch is a new way to close the semantic gap using visual-only feedback on high-level attributes. As shown in the diagram on this slide, after the user starts the search, synthesized images that differ in attribute values are presented to the user as options. And when the user makes a selection that one option is closer to the target than another, for example, if you look at the first question here, if we pick the true on the right, then the system is able to make some kind of reasoning. It can incorporate the feedback, re-rank the images, and possibly continue with more questions if needed. By eliminating the need for user to understand the attribute, Syntharch allows for more universal image search. It further opens the potential for interactive image search to operate on unlabeled datasets. In today's talk, I'm going to follow this outline by first introducing the task, challenges, and related work. Then I will present Syntharch, our new interactive image search approach, as a solution to the problems. Next, I will explain our experiment setup and discuss the quantitative and qualitative results. And finally, I will summarize our work and reveal limitations as well as how the work can be expanded in the future. Now, let's start with interactive image search again. From there, I will talk about attribute-based search, conditioned image synthesis, and finally, image editing. As early as 1993, people has experimented with interactive image search. In Find-It, one of the earliest systems, users can outline objects they want to find in the database, and the search system then compares the color histograms to get the search results. ImageRover, published in 1997, is the first online image indexing and search tool that incorporates relevance feedback. However, it still uses low-level features such as color and texture, just like how color histogram is used in Find-It. In recent years, relevance feedback has been shown to be more accommodating to high-level concepts. For example, in Qflix from 2008, Qflix is a web image search application which allows users to create re-ranking rules based on concepts such as scenery, portraits, sports, actions, and so on. It is using those more high-level concepts as opposed to low-level features. As discussed previously, interactive image search using relative attributes is a promising approach for CBER tasks. Using relative attributes as opposed to binary attributes further allows for comparative feedback. In the attribute pivot work, Kowalska and Gorman proposed building a binary search tree for each relative attribute and to search within those trees. Recently, there has also been explorations with other feedback forms, including free-form attribute feedback, sketch feedback, and dialogue feedback in natural language. Our previous work relying on semantic visual attribute used textual form of feedback. Our method differed from those previous work in that in Syntharch, our previous attributes are expressed only in visual forms. In order to ask questions visually, we need to generate the image options. So next, we explore image synthesis. Synthesis of realistic images has been greatly empowered by deep generative models, including variational autoencoders and generative adversarial networks. In variational autoencoder, the input is mapped onto some latent space by a probabilistic encoder and then reconstructed by a probabilistic decoder. Again, the generator accepts the latent vector and outputs a synthesized image. It functions similar to the decoder in the VAE model, but instead of minimizing the difference between the pixel values of the original and the reconstructed images, GAN also has a discriminator which distinguishes input from the distribution of the real samples and the generated result. Therefore, in essence, training of a GAN is a minimax game to some sense. The generator wants to trick the discriminator, and the discriminator counters the generator's effort. Deep convolutional generative adversarial networks, largely based on GAN, was introduced in 2015, and this class of network is capable of synthesizing highly compelling and detailed images. For Syntharch, we decided to use GAN to generate the feedback options. For image editing, however, unlike VAE, which naturally comes with an encoder, GAN lacks the capability to project real images onto latent space for reconstruction. To enable GAN for image editing, we'll have to build the encoder on top of the GAN architecture. Invertible conditional GAN, or IC-GAN, introduced encoder networks trained by random datasets created with the generator. Conditional C-GAN networks enable modulation of the output image based on different kind of parameters, represented by the Y vector in the diagram on the slide. Notice that conditional vector in C-GAN is additional input to the generator. In practice, given an image, we can use the encoders to estimate the latent vector z and the conditional vector y, and then use the generator with modified y, we denoted by y prime, to edit the image. Now we present Syntharch, a novel interactive image search approach. In this section, I will expound on the design of Syntharch and highlight its major differences from previous systems. Syntharch leverages a conditional image synthesis for collecting more informative feedback. It comprises two modules. A pre-processing module that performs a two-stage training for every image database, and a search module that interacts with the user who wants to retrieve an image from a pre-processed database. In the following slides, I will discuss each module, specifically the two training stages of the pre-processing module and the search method, as well as the ranking method of the search module. During the first stage of the pre-processing module, we train the generator network adapted from the rank GAN. At training time, three networks learn simultaneously. The generator takes in a latent noise vector z with an attribute vector y and output a synthesized image x. Note that on the diagram on the left, the attribute vectors denoted by r, that's from the rank GAN paper. I use y for consistency. The discriminator takes in an image x and outputs the likelihood that image x is real. And finally, the ranker takes in an image x and outputs the relative attribute values for x. The attribute vector y of size n is a uniform distribution from -1 to 1, whereas the latent noise vector z of size 100 is a normal distribution centered at 0. All three networks are regulated by binary cross-entropy, the BCE laws, and the laws of the discriminator and the ranker serves as a feedback to the generator to produce more realistic images that obey the pairwise rank at the same time. By the end of the training, we will be able to learn a multi-dimensional attribute space where the attribute vector y lives in. On the left-hand side of this slide, we show the network architecture of the rank-SIGA network. Specifically, the discriminator and the ranker share the same architecture except for the output layer, where the ranker has a dedicated ranking layer for each attribute. On the right-hand side of this slide, it's a demo for the generator network trained on image database of shoes for attributes. We'll talk more about the image database later. In this demo, we fix the latent noise vector to be some random value and modify the attribute vector y in 4 different dimensions. And you can see how the output image is changing as a response to how we are modifying the attribute vector y. We implemented the encoder network proposed in iCGAN to approximate the latent noise vector z and the attribute vector y. Given an image, this network is regulated by the mean square error, the MSE laws, shown on the top. The bottom. We denote the encoder for the latent noise vector z as EZ and the encoder for the attribute y as vector EY. Using rank-SIGA network with the encoder, we can perform image reconstruction and image editing. On the left are some of the image reconstruction results. In each pair, the image on the left is a real image from the searchable database, and the right image is reconstructed image generated with y and z approximated by the encoder. Well, not all the detail like colors and fine patterns are fully preserved in the reconstructed image. The general shape and the style as dictated by the labeled attributes of the datasets are similar within every pair. On the right-hand side are some of the image editing results. Each row is a group that shows the original image and reconstructed images. Reconstructed image followed by the edited images in 4 different attribute dimensions. By now, I finished discussing the image synthesis and image editing methods empowered by the preprocessing module. Next, let's talk about the search module, starting from the overall search approach. Recall that in the attribute pivots work, the pivot image was chosen for each attribute by going down binary search tree. In Syntharch, because we have already built a multi-dimensional attribute space in the previous steps, we can now search just within the space. And again, recall that the attribute vector is in the uniform distribution from -1 to 1. The initial search range for each dimension is therefore also from -1 to 1. As shown on this slide, we can then transform the 3 binary trees into a cube of 2 by 2 by 2 in a 3D space, or the number of dimensions would just be the number of attributes. For example, starting from the initial state where the center of the attribute search range is at the origin 0, 0, 0, we want to release feedback on the first attribute dimension. To generate the 2 option images, we decrease the value of one of the attribute vector's first dimension by 1/4 of the range and get y1 at negative 0.500, and then we increase that of another attribute vector by a quarter of the range and get y2 at 0.500. To generate the feedback option, we also need a noise vector z. Instead of setting z to be random, we search for the image from a database whose estimated attribute vector is closest to the center of the range. In this case, it's the origin. And we measure the closeness by Euclidean distance, the L2 norm. Now, the user can choose between the two generated images with different attribute values. For the sake of this example, say that the user chose the image with attribute vector y1 rather than y2. Then we know that on the first dimension, the expected value will be closer to y1 than y2, and we can therefore reduce the search space on the first dimension accordingly. Specifically, here we reduce it by a third instead of a half as in a regular binary search. This allows us to have some tolerance when the user makes a wrong decision, potentially, or the decision might be hard. Following this example, the new search range on the first dimension will now be from -1 to a third. And then we can move on to the next attribute if needed. After we obtain the relevance feedback using the range searching method described on the previous slide, we still want to produce a ranking of the database images according to their relevance, so we can get the search results. To get the ranking, we calculate the probability that each image is relevant following a method modified from that in the attribute pivot work. Here, we use a sum of log probabilities rather than a product for numerical stability. Each probability is estimated via the plus method, in which the sigmoid parameters are learned from the pairwise comparison labels. We run the relevance prediction model on all images after each iteration and sort the images by their probability of relevance to get our search results. And this concludes our search module for Syntharch. Moving on to section 3, in this section, I'll talk about the user study we conducted to evaluate Syntharch performance and to validate our hypotheses. For our experiment, we evaluated Syntharch with the UT-ZAP50K database, a public image dataset of shoes which contains 50,025 images for relative attributes and 6,751 comparison labels. Each label contains two image indices and attribute dimension, indicating the first image having a stronger strength in some attribute than a second image. We quantify the image performance by the accuracy score, which is the percentile rank of the target image probability of relevance. The percentile rank is defined as the percentage of images in the search database that are ranked lower than the target image in the search results. The higher the percentile rank, the closer we are to the target image. For each experiment section, we run 30 image sessions in total. In each search session, we ask 12 questions. A sample question shown on this slide comprises of the 3 images here, the target image to search for, and 2 options labeled 1 and 2. We also have additional rules that if the target image reaches the top 20 of the result, then we terminate the search and note that we have already found the target. There are 2 hypotheses that we would like to validate regarding the Syntharch method. First, we want to evaluate the benefits for image editing. The change from using textual feedback to visual feedback itself does not warrant the use of image editing and synthesis. And specifically, given 2 attribute vectors y1 and y2 as described in the approach section, we don't have to generate the options. Instead, one alternative approach is to retrieve 2 real images with the closest attribute vector to y1 and y2 and let the user pick between the two real images. However, unlike the image editing result, which only differs in the attribute expression when the latent noise vector is fixed, we are concerned that the other varying details might confuse the user. Moreover, the distribution of real images might be sparse in certain regions of the attribute space. In that case, we might end up retrieving the same image for both options. The second hypothesis is that the range search indeed benefits the search. And given k attributes in Syntharch, we build a k-dimensional attribute space during the preprocessing. This differs from the approach in attribute pivots, which is to search on k separate binary search trees for those attributes. The intuition of maintaining a search range despite not needing it for ranking results is that synthesized feedback options can therefore be more realistic, and the subtle differences can then better reflect the attribute value variations. However, we can still have an alternative method which gets the pivot images from the binary search trees and use two image options with a certain attribute edited from the pivot image to a greater degree and to a lesser degree to collect relevance feedback response regarding the attribute. For the user study, we implemented both alternative methods. And recall that we ran 30 search sessions during each experiment session. 10 of them will be using the original Syntharch method, 10 of them will using the alternative method which retrieves real images as options, and the rest 10 will use image synthesis, but search a binary search tree for each attribute. We asked 8 people to complete live experiment sessions for my user study. From them, we recorded 240 search sessions. That's 80 sessions for each method, and a total of 2,876 relevance feedback responses. The plot on the left of the slide shows the change of the percentile ranks for all 3 methods as the search progresses. We observe that while the rank of the target over time has a general upward trend for all 3 methods, that of the Syntharch method, represented by the blue line, exhibits a more consistent increasing pattern and has the highest ranking percentile among the 3 methods. In particular, we know that by the end of the 12-question trial, the target image is at 71% for Syntharch, at 70% for the Retrieval method, and at 56% for the pivot method. In each specific search session, the percentile rank decreases if and only if the user makes a comparison contrary to the model, which we refer to as a confusing feedback. Note that we use the term confusing here to indicate that the system will be confused. It does not suggest that the user making the comparison is at fault. To understand the conditions of receiving confusing feedback during the search, we look at some of the specific search sessions where aggressive percentile rank declines take place. For example, the plot on this slide shows a sharp declining trend for the percentile rank for the retrieved method starting after iteration 2 until iteration 7. On the right-hand side are the feedback options and the user's choices. The user's choice indicated by stars. Observe that during the session with the retrieved method, the feedback options remain the same starting from iteration 4. This is due to that if the previous choice led to a region of attribute space that is sparse with real images, regardless of the variations of the attribute vector, the nearest image will always be the same. When the 2 images in the pair are too close to distinguish, well, in this case, they are exactly the same, they're identical. Users are instructed to make an arbitrary selection, meaning that they will provide confusing feedback half of the time. We know that this concerns with the overall distribution of the image attribute space rather than the numerical value in one particular dimension. And in this case, at iteration 4, when we ask about the 4th dimension of the attribute space, the numerical difference is actually 2 times a half, which is 1. However, we still retrieve the exact same image for both options. Now, let's look at another example. Here, the drop of the percentage rank happens to the pivot method in iteration 4 and 5. Specifically, at iteration 4, the attribute being considered is comfort, with the first option reflecting less comfort and the second option reflecting more comfort. However, the expressions of the shoe's comfortness for the neighborhood around the target image and that around the pivot image at iteration 4 are quite different. Increasing the comfort attributes actually alters the shape, which turns out to be visually more similar to the target, whereas the target image has a comfort value a lot less than that of the first image. This tricks the user to make a confusing feedback. Here, we see another example of the same attribute as manifested differently in different neighborhoods. When considering the openness of shoes, the change of the attribute value in the region around sport shoes affects the shape of the opening of the shoe only. However, for high heels on the bottom, we can almost see the shoe being shrunk in width and as we decrease the attribute value. This pattern most likely accounts for the confusing feedback from the user and the inferior search performance using the pivot method here. To summarize, the study shows that Syntharch method outperforms both alternative methods on average. In particular, using synthesized as opposed to retrieved images allows Syntharch to have more precise control over attributes in regions where the attribute space do not have sufficient image sample coverage. At the same time, range searching leads to attribute expressions that are more likely to be consistent with those near the target image. Consequently, the combination approach in Syntharch, leveraging both image synthesis and range-based search, has the best performance in all three methods tested in the user study. Therefore, the user study results validate both of our initial hypotheses. Nowadays, interactive image search systems rely predominantly on attribute labels and comparison feedback in the textual form. In this work, we explored a novel approach using only visual feedback to accomplish the same task. We propose Syntharch and then use a user study to confirm the design decisions that using image editing over retrieving real images for feedback options and performing a range-based search in a multi-dimensional attribute space over searching in separate binary search trees both led to better search accuracy. In this final section, I will discuss the limitations of Syntharch and how the work can be expanded to overcome some of its limitations and to solve a more generalized problem. In case study 1, we saw the percentage rank of the retrieved method dropped when we entered a sparse region of the attribute space. In fact, if you recall, the rank of the Syntharch method also dropped around the same time because without enough training examples, the synthesis space around the region might not be smooth, and we will end up having low quality editing results like the one shown on this slide. To overcome that, we look for ways to improve the image editing quality. And one possible direction is suggested by Zhu et al. In 2016. In their work, they explored using the generator output as a constraint for image manipulation operation through morphing. Because the result image not directly generated, but rather morphed from real images, the manipulation outputs can be photorealistic. By improving image editing quality, we will be able to greatly reduce the amount of confusing feedback we get in Syntharch. On the other hand, at training time, we still need binary labels representing pairwise attribute comparisons of images in the dataset. Using these relative attribute labels not only make it harder to learn a more uniform attribute space, but also qualifies the generalizability of Syntharch as most image datasets don't come with relative attribute labels. Because Syntharch uses only visual feedback, it does not need semantic attributes which can be understood by the user in words. And I think task of choosing non-semantic attributes can be automated. One possible approach has been suggested by Perec and Guaman in 2011. They explored building semantic attributes that are discriminative for discrete class labels. For our purpose, since the attributes do not necessarily have to be nameable, we can just take the top few attributes that are most discriminative and start Syntharch training from there. If the attributes can be learned in such a way, then the preprocessing module of Syntharch will only depend on binary attributes that are much more commonly found in datasets. Further, if we can learn the attributes from the space of the latent noise vector Z, then we won't even need binary class labels to bootstrap the attribute selection process. In that case, the preprocessing module can be completely unsupervised that gives, given any database of unlabeled images, regardless of the content, we can perform interactive image search on them, making it more universal and much more helpful in real life. Lastly, recall that in our current design, the preprocessing module, which is responsible for attribute condition image synthesis, and the search module, which carries out the search, are treated as two independent parts of the system. However, it might be possible to combine the synthesis objective and the retrieval objective to train them jointly. This idea can help us to build an attribute space that is better distributed for attribute editing and search. This concludes my presentation today. Thanks you again for joining me. I will be available during the live Q&A session for any questions.